to introduce Martin Frasch, who's travels the world, but it's mostly based in US. But he was holding a visitors research position in Munich this year, right earlier. So I'm a little bit confused. So he's a long-term friend and collaborator and a pioneer and a visionary for better technologies for fetal monitoring. So that's my topic of research as well. So I'm very, very happy to have Martin visit us for 2 days. So he will talk to us about his global visions, I think, about AI and fetal monitoring and beyond. So I leave that to him.
Thank you. Hi, everybody. I want to start by thanking Antonia again for the kind intro and for you to be interested to listen to the story. And when I'm supposed to start with these things, somebody last year taught me that conflicts of interest are actually more opportunity, which means you actually care to take things all the way to people. And so I've done this a number of times. And, yeah, so the perspective that I take is therefore one of asking, there is an algorithm out there, will it ever make an impact? And it's not me saying that there is not a value of theoretical science, quite the opposite. I'm a huge fan of it, but that's just where I am with my approach to this at this point in life. And yeah, so the talk will consist of two major parts that are very imbalanced. One, the larger chunk of the talk is on what AI can do for developmental neuroscience, which is just my way of generally referring to monitoring fetal brain development, fetal injury, detecting risk for fetal injuries before they happen, hopefully, which is really what we all want to achieve, Tonya, I, and many others. And so in the framework of calling it part of developmental neuroscience effort, there is a second part of the talk that I'm also quite excited about, and that is to ask the question how developmental neuroscience may inform new approaches in AI itself. And so this will be quite a bit less in terms of the number of slides, but to me, basically equally exciting, and I hope you'll take something from that as well. So diving now in the first part, which is AI ML for fetal brain development. And so the problem, as I would like to present to you, is that the pregnancy itself, in a sentence, is essentially a black hole at the moment, anywhere in the world. We have no idea what's going on for the most part, and in part, it's a justified approach in terms of allocation of expenses in healthcare for the services, because it goes well most of the time. So what's the worry? However, when it doesn't go well, the repercussions are extraordinary for lifetime. Interestingly, over 90% of the babies who are making it, despite an injury, have a life expectancy the same as everybody else. So the burden and missed opportunities for the children, as well as the parents and society, are extraordinary. And so I think that's why, if for no other reason, it is important to address this black hole situation. So you really have a status quo where there is an uncertainty on the individual basically level of what we know about the fetus when the mother and the baby come for delivery, and there is also a disconnect between the information obtained in the side of the obstetrics and that obtained in neonatology and postnatally, and that, well, it is a pain to try to connect information pre-pregnancy, in pregnancy, intrapartum, that is in delivery, and postpartum. They're often siloed in different departments and with all the complications that come from it. It doesn't make any sense, but it's because the traditional disciplinary approach has developed that way. So that's just been called out so many times as an issue that impedes the research on such data sets a great deal. So I would always, I like to approach a question always from an angle of what, first to ask what you would like to know, but then also ask what are the limits, hence epistemology. And so one of many ways to put it is in a quote here, despite the plethora of the patterns that we see, the principles are typically not that many. So it's always exciting. And hence, again, the theoretical part of the research is always as important to find what are the principles that that are hopefully governing the patterns that we are trying to detect. And so it's also important to keep in mind the principles that we're looking for here are not limited to a particular scale. So I'm not talking about how the genes are organized in contrast to how the heart rate is organized. These are something overarching that we may use to describe the integrative physiology at all scales. And so we may or may not get to this in the talk. And then, of course, which is where the AI comes in, can AI support us in identifying the order and applying this understanding to this healthcare problem? So,
Sorry.
Yeah.
Can I just, this is Abdul Salam, the theoretical physicist.
Yep. Yeah, that's the one. Yeah. So I will start with a few slides on AI. Not too many, since again, most of you have a good idea, and those who are online as well, but just to get us on a certain common page and then go through several approaches of applying the deep learning algorithms for detection of patterns in cardiotochogram data, abdominal electrocardiogram data, so different ways to record the fetal activity non-invasively, and then some approaches around feature engineering on those data, and some symbolic logic approaches, which is going to touch on this attempt to find the underlying principles that may be governing on different scales the behavior of the data that we're looking to understand. And then, of course, coming back to the constraints that may exist on the data and implications for future work. And then we'll switch to this other part of the talk. So let's dive in. So artificial intelligence is good at capturing the relationships between the data, including and especially those that are not important. So it's not a panacea, but it can do something that we humans are intrinsically very bad at, namely discovering relationships, linear and nonlinear, that are difficult to spot with the human eye. As you know, AI, as we know, it has been around for now almost three-quarter century, and it's only in the last, well, since 2018, really, that we're talking about the deep learning as such. So it's quite new, and there's some recommendations here for some of the articles you may consider, some books I found kind of informative to look at. So ML in general is like with all basically models, it depends on what you put in. So if the data you put in is not good, you get the garbage out, the predictions will really not scale, and so on. However, there is an interesting feature or a property in ML, and that is the ability to combine the models that by themselves don't really do well at, let's say, really low R2 or AUC values, right? But together are able to yield very performant basically models. And so that's something that I often see the reviewers not understanding if they come from a non-ML background and they see, but your individual performance metrics are so bad, why are you doing it? So that's an intrinsic property of such ensemble models, and an exciting opportunity here. So in general, what MLOI does is the classification, regression, and forecasting. That's what it does, right? So, and it's not always a black box. A feature importance can be used to inform the models, to build the models, which helps understand why the models do what they do. And as Eric Topol pointed out in this article here, we do have a bit of a bias to ML. We have been accepting for decades the pharmaceuticals, so we have no idea how they work. And yet we ask a lot from AI ML and want to know exactly why they do what they do. There's a bit of a discrimination going on there. I just found it amusing to keep that in mind. So there's different ways to use deep learning, of course. I picked out two, what I call the bottom-up approach, the other top, the converse of it. So what I mean is you can start with expert knowledge and build machine learning on top of that, or you can start with kind of a blind approach at applying the models and then extract interpretable information from that. And there's also basically everything in between. So here in this approach, we use computer vision, which is really where the deep learning onset was in 2018 or so. And Antonia's group has done a lot of work using also the CNN, the convolutional neural networks. It's an auspicious approach because it's one of those we know basically most about, because it's been around for so long in comparison to some other algorithms. So here you see the fetal heart rate on top and different activity on the bottom. And what we've done is we used expert knowledge to label and to train a convolutional that is the neural network to detect a number of features in fetal heart rate and uterine activity at the same time that together were defined to represent what's called a point A. And point A is a time point in delivery process where an intervention would allow to essentially stop the outcome from spinning out of control towards a bad outcome. So it's actionable. And so here we simply show that a combination of such expert labeling can lead to a very high performant basically system, as you can see with AUCs here being excellent. The downside of such approach is you need the expert labeling to teach the system, and that's a bottleneck that cannot be neglected. The labeling. So another example of an approach here is kind of the opposite approach as I indicated, where you take the machine learning to start with and then extract the features that may explain why the model works the way it does. And this is here applied in a study on antepartum data, and the study was really conceived by the colleagues at the Technical University of Munich, Dr. Silvia Lobmeier and Dr. Marta Antonelli. And I've been fortunate to be part of it on the data analytical side. So the layout was to collect the data in the third trimester and to then collect, so this was the abdominal ECG electrocardiogram, which is done basically on the abdomen, and then to collect some outcome data at the time of delivery and some follow-up data of the second year of life. So maybe of some interest in particular to some of you as you indicated interest around the neurodevelopment. What I will focus on is there's been a screening, of course, happening, and the enrollment. We ended up with about 180 patients from which we had the data. And so that's on a data set where you have one patient on the stress side and the matched patient on the non-stress side. So it's basically enriched for stressed outcomes, for the outcomes from the stress moms. And so the original discovery was completely on the signal processing side, no ML involved, where we found that the heart rate of the mother and the heart rate of the fetus seemed to synchronize when the mother was exposed to stress in the third trimester, and that was not the case in the pairs where the mother was not stressed. And I should say the stress exposure was identified by a psychological inventory that describes a subjective experience of stress, which is what the stress really is. It's subjective, right? So it's not about the cortisol levels, but how you feel about life. So we started out then using that as a feature in subsequent ML models. And so that's where this evolved. Just wanted to give you a taste of some explainable ML. So decision trees can be often very informative to understand how ML models work. We can literally kind of see how the model thinks, given the value such and such, where you end up with stressed or non-stressed. And what's interesting, and this is really all I would like for you to take out of this, you can do a feature importance ranking, and so you can see if you add more information, so not just the heart rate variability metrics, but also biochemical characteristics like the cholinesterase activity in the maternal blood, or sociodemographics like BMI or the cortisol levels in maternal hair at the time of birth, they can all add to the model's performance to detect the diets that show the stress levels increased. But what's interesting here, we found that the heart rate variability alone, that is the synchronization index that you just saw with the entrainment occurs, was actually more effective than any other set or the combination of the features. So sometimes, and this is important because you will hear a lot if you haven't, that the social determinants of health are very, very powerful in predicting outcomes, often much better so than genetics or any other physiological metric. But there are instances where some of the biometrics themselves can outperform all of those. And it's not necessarily intuitive when that's going to be. It's worth exploring in every case. That's really my takeaway message from here. So switching now to the next question, we ask, well, this is all very nice, but there's a lot of basically signal processing involved and MATLAB or porting it to Python and then doing all these computations to extract the synchronization indices. Can we just do it from raw ECG with no explicit computation involved? And that's what we've done here. This is a deep learning approach where raw ECG was ingested into a network with architecture shown here. It's called the self-supervised approach where you don't need to label the raw data. The labeling occurs internally inside the model. It extracts the labels and then applies them. I cannot go in detail, but the information is there. It ultimately uses the labels to make a classification task or a regression task. The classification task can be take the raw data, raw ECG data, and tell me if this is a mother-fetus diet from a stress group or a non-stress group. Or it can say, based on the raw data, tell me the cortisol or the FSI value, the stress index value, or some other outcomes across a continuum. So that's the regression task. And so it did really well in those. And what's interesting, it did so best when it took the maternal ECG by itself that was basically trained on public data set, not on maternal ECGs, but on ECGs that were input in the emotion recognition network, that's what it's called, that were not from the pregnant moms, but think of an age-matched adult ECG. So that indicates that we may have come across some features of electrocardiogram that are not interpretable because it's a deep learning network and it's really hard to look inside, but seem to indicate the stress status and some other characteristics of the chronic stress exposure from raw ECG alone. And so that's really exciting and led to the paradigm that we're exploring now at the two, which is to use raw ECG data with this deep learning network, which by the way can be run on a smartphone if you wanted to. As you may know, the TensorFlow based architectures don't take a lot of computation once they're basically fully trained. They can be run on edge device. That's the beauty of it. And potentially to use this approach to inform the behavior of the moms, to make them aware what their effort to reduce the chronic stress does to that index, extracted from this deep learning network, and then hopefully to improve the outcomes by allowing such increased awareness of the chronic stress levels over time. That's something that's ongoing. And it's really the result of this deep learning approach because it makes it a lot easier to deploy. So on to the feature engineering. So here, this is, as I indicated, it's kind of a mix of the bottom-up and top-down approaches. You have some expert thinking behind it and some ML on top of it. And so the case in point here is the question that comes from the DOHAT space. DOHAT is a very English thing. It's developmental origins of health and disease. I say very English because the origins come from David Baker's work several decades ago, I think already, maybe 30 years ago now. And so it was among the first to indicate that early exposure in utero to adversities can lead to increased risk of things like diabetes or cardiovascular disease. And so, of course, now it's far more widely accepted and explored, including also the neuropsychiatric disorders. So it's a broad concept. Sometimes we also call it the fetal programming idea. So several examples were we applied to ML in the context of this paradigm. One was in a preclinical study with colleagues at University of Cambridge that have a unique setup where fetal sheep hearts can be mounted in an apparatus independently and studied for their physiological features. After inside the fetal sheep, they were exposed to hypoxia over time. So here you're able to ask the question, what impact does the chronic hypoxia in utero have on the cardiac physiology or the heart rate variability of the heart itself, which is a contributor to the heart rate variability in a body when the heart is still inside. And the other question was then the impact of the chronic hypoxia as it may occur with the Zika virus infection. You may recall before that pandemic, we had another one called the Zika pandemic. And so this affected especially the global south more so. And so affected a lot of people. Here, the cohort was a number of kids that were born to the moms diagnosed with Zika, but without the microcephaly. So we asked, are there more subtle alterations to the cardiac physiology or to their HIV that can be basically measured non-invasively, which can tell us something about this in vitro exposure. And then another study was a convenience sample from autistic spectrum disorder children at the age of 8 years old compared to children with the conduct disorder and depression. And so I'll show you the results in a second for all of those and how they may add up together to some sort of bigger understanding. What's important to point out when it comes to feature engineering of heart rate variability, and that's really true to all physiological time series, what makes it so hard to compare the papers one to another is that the pipelines for the processing steps, which can be quite complex, just like with any other analytics, they really need to be explicit and they really need to be done in exactly the same way. Otherwise, the comparison is really a waste of time quite often. And so if you do follow it, and we've been fortunate to use a particular system for over a decade across the studies in animals and in humans, so we got a certain workflow down, which allowed us to take the data from animal models to humans and back and to compare it. You can extract over 100 different features of the heart rate variability and use them to build understanding of the patterns of the heart rate variability that are changed due to adversities in utero, for example. So not intending to walk you through the heart rate variability features, but this is a study where we found that if you take out the vagus nerve in a pregnant sheep model of fetal physiology out of equation, the 4 HIV metrics that are changed are mostly not the metrics that most people look at, not RMSSD for sure, which is what everybody thinks about when it comes to the properties of the vagus nerve. And a symmetry index, interestingly, which is an interesting one, is used in sepsis scores in the neonates in clinical settings. So that was interesting to see that it pops up. So it's just a flavor for you how you can extract potentially features of interest through the feature engineering approach and heart rate variability. Having built some understanding of the different alterations that occur in heart rate variability across different signal analytical domains, the frequency domain, time domain, scale invariant domains, and the fractal properties, and complexity domain, we were able to select sort of in a domain expert way certain features that are listed here, and then apply them to this data set in 8-year-old kids, some of which had a diagnosis of ADHD and some of which had other diagnoses, as you see here, the conduct disorder, depression, and typical convex hits. And so there is an incredible, it was an exciting degree of success that we saw in the performance and classification of the kids across the 4 different sub cohorts. And of course, the hope here, and this is a call for all those who are interested to pursue this further, is to take it back in time and to really try and identify these characteristics as early as maybe 1 year of age. Because as we know, one of the key challenges with diagnosing ASD is that it's diagnosed way too late, almost two times too late as we could. Average age of diagnosis is about 4 years of age. A parent typically sees it in a kid when they're maybe 1 to 2 years of age. And so this window that is basically last to intervention is a huge opportunity that's being missed. And
What is the percentage?
what's that?
What is the
Oh, that's just the feature importance list of the
percentages?
is how much they contribute, and then sort of as up. Yeah. So this is a classic. Yeah, sorry, I'm kind of skipping over that here. Yeah, thanks for asking this. And you can see that basically different domains contribute.
It's all SD2.
SD1, SD2 is the concurrent plots metrics. Yeah, and then some other metrics, and so basically it's a mixture of different domains performing together. Important to note, when it comes to monitoring the health of a fetus, it's always 2 for the price of 1 or 1 for the price of 2. Depending on how you look at it, you cannot ignore the maternal health, since of course the maternal health impacts the fetal health and outcomes. There are studies indicating that non-invasive monitoring of maternal heart rate variability can also be an indicator of the onset of hypertension or the diabetes in the mom. And so those are really important opportunities that I think are not explored as much as they could to help inform the follow-up of the moms on the individual basis before the clinical symptoms occur of these conditions that impact both the maternal and fetal morbidity and mortality. So that is then the summary here of what I wanted to share with you as an example of feature engineering and expert-based approach to building ML models on data about the fetal health and outcomes. Something that I would like to stress, which is I think not so widely known when it comes to EPG sensors like Fitbit type, basically wearables or electrocardiograms, is the impact of the sampling rate itself, with which the heartbeat is basically sampled on the quality of the metrics. It's a considerable confounder or a determinant of the quality of data that we use and the kind of the values that we obtain when we compute the heart rate variability metrics downstream. And so there's been some studies on that that are shared here, and there are some ways to engineer the heart rate variability metrics in a way that work around this limitation, but it's basically important to be aware of it when you go into using bit-to-bit data to extract features that you use for your models in a broader sense. So symbolic logic approaches are fun because this is really where AI actually began before we switch to the statistical approaches that are now the mainstream. And they're still actively used. Most deep learning models that you see today all have symbolic logic built into them. They're not just so widely advertised as part of the approach. This is an example that was an incredible fun and honor to work with this team of applied mathematicians at York University in Toronto, where we built a model with 30 ordinary differential equations that essentially describe the process of the human labor, which is what you see here. And so it's able to generate fetal heart rate, blood pressure changes, uterine activity equivalent changes that occur over the hours of labor that matches the observational data quite well. And I would love for this to be used more because I think it's kind of a treasure trove of in silico ability to mimic what otherwise would essentially necessitate an animal experiment to get all this data. So there. And maybe we would be able to actually port this approach into a deep learning model to simplify the execution of such a model, because straight up computational execution is obviously an exercise that takes a lot of computer resources. But here, I just want to juxtapose it to the deep learning approach, because here, all properties of the system are explicitly defined. So there is now the really exciting piece that is going to take us also the most into the second part of the talk, where we will talk about what developmental neuroscience can do for the new approaches to building actually the AI itself. And what that is a story that goes back almost 100 years at least, and in part it goes back 1,000 years actually. It's this enigmatic link between synchronization of complex systems that are weakly coupled and metabolic optimization. And so these things are simply images of certain mathematical properties that have been known for a very long time. And essentially the occurrence of the frequencies of the ratios between two oscillators that are weakly coupled are more often observed than the others, and the probability of this observation of the ratios between the weakly coupled oscillators turns out to have something to do with metabolic optimization in living systems. It just does. And I think it's incredibly exciting to know that, because there's so many ways in which this can be used to link the complex behavior from the numerical side with actual physiological interpretation of underlying teleology, if you will, why it does it. So here's an example in the horses. If you put the horses on a treadmill and you record the metabolic consumption in the horses as they are accelerated on the treadmill and they change the gaits, you can see how they go into kind of like gears in a car, for those of you who still use a stick. And actually feel that. So you see these dips in the energy utilization that occur every time they switch into the regime where they're stable, then it goes up and then it switches back down. And so this multi-stability, that's a keyword here. And I cannot recommend enough this book, Dynamic Patterns, from 95. If you want to learn a little bit more about this, and yeah, feel free to take a shot at it. And so we were inspired by these insights, and so it was the second paper that I've ever done was on heart rate and respiratory rate synchronization in healthy neonates. And you can see here the quiet sleep, which you may know also as the non-REM sleep or the deep sleep, in comparison to the active sleep, or what you may know in adults as the REM state. And so it's known that the quiet sleep is the one where less energy is used, while the active sleep is the state with energy expenditure increasing. And so the ratio of synchronization between the heartbeats and respiratory movements is the classic 3-to-1, which you may recall from the Faraday trees and Arnold tongues, is the likely one, which requires less energy, while in a high energy expenditure state, the ratios begin to dissipate across the spectrum of the less likely states. And so this is an indication of a way to conceptualize the nonlinear relationships between oscillators, and it is completely basically substrate independent. That can be expressed in such ways. And so we're going to get back to this when we talk about AI architectures. So this is an opportunity, I think, for a lot of studies that could be done in the neurodevelopment, neuropsychiatry, but also potentially in other situations where you're interested in understanding the network architecture in a dynamic way. Another interesting study in this context, and it may be of some interest, maybe too, because again, you mentioned the interest in the networks. Bashan et al. In Nature Communications 2011, where they also proposed a topological approach to study the network architecture across the switching of the states in a physiological system, might apply to other networks. think, a very elegant word mathematically. So we're going to take the cues from that later in a second, really, more or less, as we talk about AI. So you have now a situation here, again, going back to epistemology, where perhaps we've come across some simplicity that may give the rise to surface complexity, as it were. And a way to think about it is not so much in a way of a magic bullet, a single biomarker or a bunch of biomarkers that are describing the system, but more a landscape where different biomarkers can be seen together in interrelational way as describing the system. So making sure we're still, more or less having a little bit of time. So I promise that I will not spare you some epistemology at the end of the run through the different approaches to AI. So as I just suggested, I think this multidimensional attractor landscape approach to think about the multivariate description of data such as the heart rate monitoring data or other multivariate data describing the system, I think is where we're more likely to identify underlying simplicity that may be governing this. So one perspective here that I find very important, because what I often hear is, I've done Doha kind of studies, people programming studies for over 2 decades, and quite frankly, sometimes it is said, well, this isn't Alzheimer's. We're all facing avalanche of people coming down with dementia. Every second individual of the 80 will have one or has one. Why should we care? Why should we fund it? It's a few kids that might get injury, and it can be depressing to hear such arguments. Well, perhaps it's important to remember that these things are not disconnected. It turns out intrauterine adversity is actually linked in a causal way directly to the risk of Alzheimer's or the Parkinson's in later life. So when conversations come up about who cares, maybe we can mention that. If nothing else matters, which it shouldn't. And what is important here, and this is also linking us back to the follow-up piece of the talk, is there is evidence that what is really the causal linkage between the intrauterine adversity and rewiring of the brain that predisposes for the higher basically risk for the neurodegeneration in later life is the biting glue is the impact of the energy availability that is a function of this intrauterine adversity. So the immune cells are not just responding to this adversity by changing the phenotype merely from a standpoint of what they do as immune cells. If you think about the cytokine production or phenotype from an immunological viewpoint, they also change the metabolic phenotype. And really, we have understood now that it's more appropriate to speak about the immunometabolic phenotype of the cells, especially the microglia, than separately about immunological phenotype. And so there is some indication here that such interactive understanding of how the glia cells are exposed to intrauterine adversity are then impacting the neurodevelopment because they're actively participating in the pruning in the brain, and then may be contributing to ultimately increased predisposition to the neurodegeneration down the road. So that's a model that we go into in this article ultimately, but that's the quick overview. There is another concept that I use all the time, which kind of came from several studies looking at the heart rate variability under different conditions, impact of sampling rate, impact of phase space structure of the heart rate variability, independence on the exposure, hypoxia, inflammation, specificity of the heart rate variability metrics with regard to different parts of the body, the brain, the gut, the heart, specificity with regard to detecting the syndromes like ASD or Zika virus, and also the species independence. That also suggested a way of thinking about the properties of HRV as indicating some sort of a code. which is what, a code is a way of communication and coding, as it were, the properties that are needed for the brain to communicate with different parts of the body and to sense the information from different parts of the body. And it's not just controlling the respiration, as we mostly think we need the vagus nerve to control the breathing. It's almost everything. It's the glucose levels, it's the sensing of the cytokine levels in the periphery, and the list goes on and on. So this is another way of integrating the various HAV properties and feature engineering into something that's physiologically quite informative, which I call the HAV code. I'll skip over this. It's just another example of how to synthesize machine learning way the different properties, not just of HAV, but also other like the social determinants or biochemical properties. So hopefully such approaches can allow us to open the black box of the pregnancies, which is where we set out in the talk, and to build machine learning models that are integrating these into a framework that is more able to predict outcomes than the bits by themselves. So it's exciting to think about opportunities in our ability to monitor the pregnancy non-invasively, continuously, as they may uncover trajectories of the neurodevelopment, and hopefully offer opportunities for intervention, existing methodologies and tools that we already have, but hopefully allow us to deploy them at an earlier time than we can today because we are flying blind. And so the wearable technologies, of course, are an opportunity here, but there are also important caveats. Some of them we touched upon, which is that biosensors, of course, are not all identical, and the data we get are only as good as the hardware that acquires them. And in the pregnancy, there is a challenge, and Antonia and the SPAM group in general have talked about it, and that is that some of the outcomes, like the brain injury, cerebral palsy, thankfully maybe 3 to 5 per thousand, so they're relatively rare. However, as we spoke about, they're incredibly impactful, and to truly build machine learning models that can uncover the risks for such outcomes at scale, we need approaches that we today really don't have yet implemented to collect data sets in the millions to be able to really train them. And so I think we just need to own that as the reality. It's probably also true for other outcomes in the neurodevelopment. Even if autism is maybe 1 in 54 kids, it's still also thankfully not quite as common. And so the need for large data sets is a big need from a public health standpoint. And then, of course, many of these technologies now can be implemented on edge, being a device such as this one, like a ring that can do a lot of computation, or a watch, or whatever. And so there are definitely technological solutions now that can enable much of the technologies that can fill this gap and that can allow us to collect the data continuously. So that's exciting. This is just a perspective of how perhaps to think about collecting data, and there's certainly many ways to do it. This is something that we've been doing with a team at the TUM in Germany, that we can collect data antepartum, even prepartum, as much as we can, social demographics and social determinants of health, and then continue collecting data in pregnancy using wearables and psychological profile data, and then data at the time of birth and the outcome data. And hopefully this is a foundation to link the early determinants of health that are easily obtainable, and this is also important for public data sets, and that can inform the strategies for allocation of the limited resources of healthcare to those who need the most. So hopefully this will decrease the uncertainty about the pregnancy as a whole and help improve the neurodevelopmental outcomes. And what's important, this is often not a one-time event, so improving maternal health has a powerful feedback on generally decreasing the risk for poor health outcomes in pregnancy time and time again. So I promised that I'll say something about the other side of the coin. So we spoke about what AI can do for developmental neuroscience. We covered some of the deep learning approaches, feature engineering, constraints that are epistemological in nature, constraints from hardware to collect the data. But we also touched on this enigmatic property between the behavior of complex systems and metabolic optimization, especially of the complex systems, and what that may do over time especially to the architecture of the brain. So this is a low-hanging fruit. It's almost impossible not to ask, well, what are actually the premises of artificial neural networks today? So let me ask you first, is the brain a neural net?
Biological neural net. No, I think so.
So the correct answer is it is not. And so it's actually only the 50% of neural net, right, at best. And I know that some people debate it, but the ratio of glia cells, or what we used to call the term the glia cell belongs in the black book in terms of the choice. It goes back to the era where we called them the blue cells, the cells that connect the rest of it, kind of like we used to call the axons the junk, and it turned out to be incredibly important. So glia cells are everything but just the glue. And so the ratio in the brain is approximately 1 to 1. And so the question is, what are they doing there in this quantity? And it turns out also the ratio is not the same from the brain region to the brain region. And there is a conservation evolutionarily across the brain regions, across the species that goes back almost 100 million years. So there's a functional importance to the ratios of the glia cells and the neurons across species, across the brain regions. So definitely more than just the glue. Interestingly, the human astrocytes are very different from astrocytes in other animals, even in the primates. We mentioned that over 2 million synapses that they're linked to in a human brain in comparison to just over 100,000 in a rat. So definitely a very different cell. And so what's interesting, we have come across over the years to discover that the energy constraints that are mediated by the glia can change the way the neuron cells actually fire. So the coding of the neuron cells is impacted and shaped by the energy constraints that are mediated by the glial cells. This is a nice image that just came out probably like a month ago from Allen Institute. It's an actual image of a pyramidal cell in teal color. I think if I can come right in. And the green is the glia cell that is encompassing it and is basically sensing the state of the cell. And the pink are the synapses, and of course, dendritic synapses that are tens of thousands. So you can't really think about the brain as just a neural net. We definitely have built AI as a neural net on a premise that's over 70 years old. And we call it artificial. It is artificial, but it's definitely not very much to do with the human brain. And I just want to establish this as a baseline. I think it's exciting because there's so much we can do to maybe build more intelligent AI. If we inform it by what we know now from a developmental neuroscience perspective. So now I wanted to zoom in on the neural architecture search because that's really how all these complex architectures are found, such as the ChatGPT, which, well, if you haven't been in a hermit lifestyle, you haven't heard about it. And even then, you probably heard it.
Something two talks on this seminar series.
Right.
The algorithms behind.
So behind all of this, right, is how to find an optimal architecture to perform a certain task. So that's called the neural architecture search, or NAS. And typically the idea is like this: you have a search space, OLID or Big A, which is all the possible architectures that can be. Then you perform a strategy, which is informed by domain, expert knowledge, and some other constraints within this bigger space to find architectures that might be best for the problem that you're seeking to solve. And then you have a feedback loop, which is on this side, which informs the way to measure the performance of all the possible subsets of neural architectures to find the best one for you. So far, the way this has been done was employing essentially the same approach that is done across ML in general, which is essentially decreasing the delta between the prediction and the value that is actually there. So decreasing the prediction error, right? So that's optimization around this. And just in case you think I'm making it up, I asked ChatGPT. It's real. This is how ChatGPT does it. So really, you can ask it everything else that I'm talking about when it's retraining from 2021 to.
In the heads of my PhD long ago was about optimization levels behind training. That's why I'm
yeah. So it is impressive.
You didn't know that, I think.
No, but that would be something to talk about over a lot of alcohol, or coffee, or tea, that is. But yeah, so now I asked ChatGPT, it's real, so you can believe everything I say now. So I want to bring it back now to what I showed you, and this will not be as many slides, by the way, because I know the time's advanced. This is a lot less slides. So evidence piece number one. So what does the brain do that indicates to us that there is a value to optimizing performance of neuroglial architecture, which in a way the brain is, and not just on decreasing the prediction error, but also on constraints for the availability of energy. One case in point is the difference in oscillatory properties of physiological data like the heartbeat and respiratory rate in quiet sleep, which again is in this classic 3:1 ratio, to the active sleep, which has this spread of the phase ratios. And so I would like to introduce here a concept that you may or may not have heard about. It's called the collective basically variable, is the phase ratio. So you don't really care so much about what the data is as much as what the phase is, the phase relation between the time series. It can be the neuron 1 and the neuron 2. It can be a network 1 and a network 2. It can be a deep layer 1 and a deep layer 2. It can be whatever. It's the you need to identify the variable that describes the behavior of the system over time, and in that case, it's the phase. So that's something that comes from a theory that I'm going to show you in a second. It's called the dynamic patterns theory. So there is a concept called the energy allocation theory in physiology, which took it up for the human physiology or for the physiology in general, indicating that energy allocation constraints are in fact a driver for the behavior that we see in the wakefulness and sleep states. Put it very simply, and not going into this rather complex diagram of what actually the outcome of this fundamental principle is. So, and the other is the figure that you just saw, which I'm simply bringing back now in the context of the neural architecture search. If you think about our lifespan as a neural architecture search, from optimization down to degradation, or hopefully not so much, then you can compress it from an AI standpoint into into the process of optimizing the network architecture for a series of tasks that we're basically faced with over a lifetime. And so it is for sure that energy constraints are a factor here. And it's interesting what's actually more important, the energy constraints or the prediction error. That's nothing, I don't have an answer to that, but I'll attempt to summarize it in a second. So, and then again, you saw the horses from this book. There is a wonderful science paper that I can't recommend enough. Just a few pages here, Schoner and Kelso, 1988, that goes in depth but incredibly concisely into this idea. So, in a broader sense, what this dynamic patterns theory states is that there is an invariance of function of behavior of such systems, regardless the material substrates. It can be a human brain, can be AI, it can be a physical system that's not a living system in a whatever a living system is. And so as long as it has a certain set of couplings, it will behave in a predictable way that can be governed in a simplistic way through an equation that looks like this. This would be the case if you take two fingers on left and right hand and you begin to tap them in antiphase. And if you allow yourself to tap them and increase the frequency, eventually you're going to be forced into in-phase. This is a classic experiment that is done to demonstrate this behavior. Of course, now you have to scale it to X, to the number of oscillators, such as in an artificial neural network or in the brain. But interestingly, there's a mathematical formulation behind it, V being essentially an energy landscape through which the system is able to move under the influence of the external force that is, for example, the frequency of oscillation in this case. So what's important here is that the function that the system does is actually not coded in a rigid way like weights in artificial neural network. It's multi-stable by design. So it's capable of switching. The same system is capable of switching into different behaviors depending on interaction with the outside. So this multi-stability, you can say, well, we have the generative systems such as ChatGPT that sort of do that, but it's not the same. It's so I think there's an interesting opportunity here. And this paper from 1988 actually talks about this. This was well before the deep neural networks. It alludes to this. So I encourage you to look into this. I think it's really interesting. So that's just explaining how this equation maps into the basins. First the antiphase on the top and then the in-phase on the bottom. So simple summary could then be that you have these energy constraints, metabolic optimization that are today ignored in artificial neural net design. And they definitely impact the brain development, also, by the way, the heart development. And this is expressed then as a multi-stability, as a property of the nets that are formed under such constraints. Could we do the same for the neural architecture search? And how would this impact the behavior of the system? So you could imagine then that the neural architecture search could be done, first of all, not just on the neural nets, but the glial neural nets. This has been done to a degree. There is a few studies on astroglial and the neural nets. So that by itself is not something that has never been done before. But what I think has never been done before is to consider metabolic constraints in addition to the task-specific demands on the network output as part of the search itself. And so maybe we would then obtain these multi-stable deep glial neural nets as a result that are capable of different behavior encoded in them under constraints of limited energy supply. So you might know when you go to the Google Translate, they've spent over 100 millions or so or more. The number is not a public number, but just read on blogs. It's an enormous number of the energy costs to make these basically models. And so there's definitely their opportunity to optimize them. And so it's interesting, the brain does this and more under 70 watts or so. Everybody saw the Matrix movie, so again, it's not me, can ask ChatGPT. But the point is, it's just a remarkable kind of a blind spot if you think about how the neural nets are designed today, and how quite evidently from developmental neuroscience standpoint, we are very much incorporating metabolic constraints into the neural architecture, the glial neural architecture in our brains. Another piece to mention, but I'm unable to go into, is the free energy principle, which is again something that came from a scientist called Carl Friston from UCL. If you haven't heard of him, please look up. We'll probably get a Nobel Prize soon. He's extraordinary. So this work on free energy principle is a broad concept, a mathematical concept that formulates how self and non-self emerges in living systems. or any system for that matter that's sufficiently complex. And the recent paper here that I cite below from 2019. No, sorry, it's this one here from communication biology. This is refusing to behave. Yeah, from communication biology from just a few months ago. They demonstrate in a neural net in the rodent, I think it is, that the behavior can be explained, the optimization of a neural net can be explained by the free energy principle. What the principle does not have is the incorporation of metabolic constraints as part of the optimization of the network. So again, there is a lacuna here that could be filled. So that could be part of the estimation approach to find the most optimal network within research space. So to sum this up, the set will be much shorter than is so today we have these opportunities from developmental neuroscience that have been seemingly ignored as a starting point to inform the neuroarchitecture search, so that we no longer just have the optimization of information, sort of the IMAX, but also the EMIN, if you will, so the minimal energy that is used for the prediction. And so there are some insights that can be taken from the free energy principle, the dynamic patterns theory, to inform the mathematical formulation of such approaches. And ultimately, interesting opportunities arise for the research and implementation, asking, is the optimization on energy more important than optimization of information? In the biology, it seems that energy is everything, and everything else kind of comes from there. I don't know if that would also work and maybe lead to completely new architectures or more effective architectures of AI. I think it's really interesting to ask, and so there's implications for a number of aspects here. And what's also important, and I will end with this, is that maybe once we achieve AI that is incorporating metabolic optimization, we might get new insights into the neuroscientific models of how the brain works, because that's how it's always been. AI began in a simplistic understanding of the brain, has enabled a lot of applications on physiological data. And maybe now we have something to suggest how to inform a new way of making AI that then again, hopefully will inform more insights into the models from developmental and adult neuroscience. So that's all I had to say. And thank you for the opportunity.
Thank you, Martin. You certainly delivered on my expectation that I will be able to follow only 10 to 15% of your impressive brain. We need to study how your brain is optimized, because it's certainly different than many of us. But yeah, I think that the more interesting part is common stuff questions. Obviously, Martin covered a lot. So what are the things that kind of resonate with you guys when we ask questions? Obviously, Martin knows all the literature as well, so he can point towards.
Yeah, let me know if there are any questions. I don't know if I should
That's okay.
try to.
No, thanks. You.
Oh, yeah, it's okay. It's only still. Yeah, 10%. Instead of so much for energy utilization. That's okay.
I got a question which might betray my ignorance. You said there is, in maternal pregnancy stress, there's a linkage between that and the psychiatric disorder. Is there any biomarker? I mean, especially, psychiatric disorder, it's a big wide spectrum, starting from bipolar, then on the other end you have schizoaffective disorder. So are there any biomarkers for that? And if there are, can we see them and can we predict the risk earlier on? Is there anything where AI can help us in?
Yes and no. I mean, it's a broad question, so I can give a broad answer first, then attempt to get a little bit more precise. So it depends first, when do you want to have them, right? So I think it's important in pregnancy, and so we've done some work on postpartum depression from a 10,000 mothers data set from an NIH study that was made available. And unfortunately, it can only be accessed from inside the US, which is one of the problems we've talked about, but should be more available data sets like these. But so we can see it's possible to predict the event of postpartum depression from data obtained before the pregnancy onset. So it's not something that's yet available as an ML model for the clinical use, but it seems to be definitely a lot of predictive information and combination of data like sociodemographics and some basic determinants of the mental health, like did you have anxiety disorder or did you take medication for psychiatric disorder? So they're very simple questions. They're not psychological inventories, even something that is a binary yes or no type question. So I think if approaching it this way seems to yield some auspicious results. There is, however, today not a clinical practice where a patient comes and you put the data into a machine learning model of clinical, in the medical records and outcomes, the risk stratification. It's based on the art of medical intuition. So there's definitely potential here from social determinants of health biomarkers fed into ML models to improve that individualized approach. And so for postpartum depression, it's interesting if you identify this at the onset of the pregnancy as an individual at risk, cognitive behavioral approaches, the CBT, the cognitive behavioral therapy, has an incredibly positive impact on decreasing the risk of actually getting it after pregnancy. But the problem is often you just don't know, you can't offer it to everybody who may or may not be. And it's not necessarily just having had a mental health issue that increases your risk. It's a combination of different things, which is again where I think it's a good example for ML because it's good at capturing these interrelations that are cognitive but not intuitive.
Are there any imaging techniques which can pick it up earlier on?
I don't know ad hoc of imaging techniques. I would say there may be some where you can identify changes. The problem with this is if you approach it this way, whom are you going to choose to image? So you can't image everybody, so you have to say
Yes.
So that to me is always kind of the chicken egg issue, right? So no question, a direct neuroimaging is a fantastic tool because that is as close as you get, but there's a constraint on the resources that would require some sort of screening to happen ahead of it. That would then, But so I don't know, but I presume there would be something there because we see this also with the studies like the fetal MRIs. We always find some of the abnormalities that seem to be indicative, but then after all of this is done, the question becomes, and how are you going to implement it in clinical care?
Thank you.
Feel free to have it's an informal forum, also online. Can you invite questions from online?
Ask audience. No questions. Yeah.
Yeah, go ahead.
Have a question. I'm very excited about the new findings that you mentioned about the HRV monitoring, so it can help us predict early developments of the child. I was wondering how mature technology is, and also the affordability of the technology, as well as the ability both internal and external of the findings. Because I'm thinking the possibility of actually using that in our programs as well, if that is possible.
I'm glad you're asking this. This is like one of the most practical things that I probably talked about. Pardon?
I'm from practice, so that
and I indicated that I think it's exciting to walk the entire spectrum if one can and when one has the time and so on. So this is I went back to the slide, so I'll see if I can answer all the points. So I think it's definitely ready for use in studies. To use something in a clinical setting, you need MDL.
I know how to make them quite the hero of the cake. because that's my fault, because I don't know the cake. I'll give them some cake so that they leave. I'm sorry. I know I'm a weird person. I'll feed them and they'll
Why don't they
go,
don't?
guys, you make lots of
We
noise.
have no cake in
That's
this.
okay.
Soon. Maybe keep the cake and don't bother. So, no, so there's the difference, right? So I think, yeah, we definitely can talk about using it in clinical studies. That's very straightforward. So we are currently using ECG devices off the shelf that are right now. In fact, in 2 days, I'm going to be looking at some of the first recordings from the study in Munich, where we're doing this prospectively in moms that enrolled as either controls or stress based on the PSS score. And but the approach can be used with other basically designs, right? If it's not the stress you're looking at, but let's say environmental or social determinants, whatever it is you are looking at, right? So you can give them ECG devices, electrocardiogram devices, record data in this way, and so it's enough to record about an hour. That was a good deal. That's all we had to do from.
Like they took half, you know. Sorry, and I need to wipe the mess. I'm too nice to people.
Oh, we talked
The
about-
food from the top.
Yeah. So I say the short answer is yes. Right, to get to the clinical application, it would be required, of course, to go through the proper studies for the the bodies that approve that it's safe to use in patients. But that's, of course, so it's at the stage of the useful research for sure. And yeah, it only requires devices that are available off the shelf. So as such, there's no constraint. We haven't used any fancy device for that. That's something that you can buy for a number of things. It's exciting.
What about the cost? Like, do you evaluate of the cost because it's sort of it's informed
Yeah.
to the some responses?
Yeah, of course. So the electrocardiogram device we use is I'll say it because you asked it, not so that you're not accused of advertising for a company. But it's a company called Lithium. Is a Finnish company. They sell all over the world, I think. And so Lithium makes a very nice electrocardiogram device. But you only need a single lead ECG for that. It's called Theros 180. And they used to cost about $600 or $800, so maybe about £500. But I think they get into the specifics. I think the prices may have come up in the past few years with supply chain issues and whatever. So I don't know what the costs are now, and the prices in the UK range are just completely different. So just to give you some, approximately $1,000 per device. I personally think it should be less. There is a Zephyr device by it's a company that was bought by the Medtronics, which is a bigger company that makes ECG and all kinds of other stuff. So a Zephyr used to cost $500. Looks like a little puck, like a disc. It's a single lead ECG which you can attach, and it can record up to 500 hours on a battery charge, which is pretty cool. And so that is another one. So there's a few options.
Did you also mention during the presentation very briefly that there are applications or are they still
Applications for
phones that can be?
there is no phone application. I mean, I can record ECG with this, just like Apple Watch or Samsung Watch, but all of these require the fingers to be pushed. It only works for half a minute or so, or however long people like to put your fingers this way. It's not really a practical ECG device. There is really no low-cost electrocardiogram device below $100.
Okay.
At least in the currencies that we're talking about.
Martin, but in this relation, how long do you need to? So my question was going to be like
Yeah,
for
how
this
long do you need
record,
to
how
get?
long do you need to monitor? Hopefully, there's obviously the urinal rhythms as well, like
Yeah.
the circadian rhythms, where you have
Yeah,
to
so
depend on
this-
the time of the day.
Yeah, so that's a really important question. So thank you for following up that there. So this was done on 40 to 50 minutes data in essentially laboratory conditions. So the participant comes and she lies down, and so you have to follow all these things. So you can't just have somebody waltz in there and here's an ECG and in 30 minutes you're done. So you have to follow certain kind of physiological steady state instructions to ensure that you're really measuring kind of a baseline condition. So there's a protocol around it. So you realistically need at least an hour for the whole thing, I would say, to have decent amount of data. Ideally, I would love to record it overnight, because really to get good data and to account for sleep states, especially, you ideally want to do the overnight recording. And that can be either at home if you can give it to the participants, or you have a sleep lab and it costs more, so usually, but then you have that.
But in this sense, it doesn't matter so much the cost. I mean, it matters, but if you're just measuring a one-off point, even if it's 1 hour or 2 hours, or
It's 1 hour per patient. Right?
yes,
Percent.
Yeah. So that would give you the snapshot of continuous data at that particular stage if it's in the pregnancy, right? And if you want to do a trajectory scan, and then you might want to do it a few times in the first trimester, second, third, something like that, or at least first and third, to get a few points in whatever it is you're looking at exposure of. We can talk more about some study design, but that's the general idea. There's
so
some
I'm
other things you
very
can-
interested in, so I work with all the heart rate data without ECG, but with a abdominal, with a cardiography, which is less precise. It doesn't give you the ECG as a complex, but it gives you the heart rate of fetus after pre-processing and averaging. So many people like Martin don't really, believe even in that signal a lot, because it cancels out a lot of the detail that ECG would give you. But this is what we have. So we have massive archives here from the hospital, and I'm most interested in labor, because that's where all the challenges to oxygen delivery to the brain are, as far as we understand today in the realities. Many things we don't understand, actually. As if I love the way you started with a black hole. It's pretty much a black hole what happens to fetal physiology in uterus today, even though we have all of the technology to go into space and into satellites and drones and whatever. But going back to so sitting on a lot of the data archives, one project that kind of died down during the pandemic, and I just haven't had the time to resurrect. But I've set up a lot of the infrastructure for us to link the hospital data to the care. It's called Care Node. So this is a 2-year assessment of the children around Oxfordshire. It's a motor and neurocognitive assessment. It's a standard. It's done to every 2-year-old around the area. And the idea is that a lot of these 2-year-olds are already delivered in the database, and their data is already harnessed as part of my other research, ready pre-processed. So all you need to do is link that score, which is available electronically in another electronic system, which is not a copy. And really look for early signs of also what happened in labor, how it links to, and I'm more interested in more milder things as well, because when we talk about neurodegenerative or type of, it is such a wide spectrum. So what we think is that the babies that are born in very poor condition due to lack of oxygen, they are anyways monitored, their interventions, their parents are aware that they have a difficult birth and so on, so they probably get more young. But many other babies are born in kind of poor condition, but quickly pick up and start breathing on their own and so on. And we tend to just give them to mom and forget about everything. Never scan, never do anything. And there is a good hypothesis out there, but it's a hypothesis of how much, what happened in labor, how they coped with it. And we have a lot of that on captured with this not precise device. But so that's something that I'm very interested in. We really should do it. And the data is there. I know the people who have that data. We have the other. We need to link into some analysis. And unfortunately, still sleeping. So I need someone to push me like you. If you want to be, you will. So these are very important questions. How do in utero data from anywhere we can get it, and birth experiences and antenatal relate to the because that will give us early biomarker potentially.
So comparative studies between these kind of markers of like data, this kind of data versus traditional biomarkers, for example, the ones that we look at like cortisol levels, are there like also comparative studies? Maybe on same population, but using different indicators.
Like this is an example, but it sounds like you have a similar cohort, and so you can definitely. So we've done it here. So this deep learning model on ECG actually is able to predict the cortisol levels from the mom from her care just before birth as well. So you can basically make it to work as a regression model. And so, yeah, it's definitely possible. And it's being done to collect these multimodal biomarkers and then use some machine learning methods to, yeah, to use them basically jointly for the prediction of the outcome. I think that's pretty straightforward at this point. So what it's saying is doing less than 20 points of talent. It's not that I don't believe CTG at all. It's just that we need to be aware of constraints and any biosensor that come with this technology. And when we choose the object-ability features, for example, that we apply to those particular sensors, we need to choose the ones that are not artificially skewed due to the data. So in the case of CTG or PPG data for the wearables, we need to be aware of limitations on sampling rate as an example.
Thank you for now prepared.
There's no reason.
Cluster.
There is no reason why you should pass these CTG query opposite. It's just that you need to choose the right features that we would get it. So yeah, definitely you can also take this. We have, I can show you if it's of any help. We have a paper, a review paper where we propose this multimodal multi-species approaches, even where you can combine data across species and modalities into develop paradigms. And yes, it's at this point pretty straightforward. Oops, thank you.
Is there anything online generally? Or?
I might have lost. Oh yeah, this is definitely dies faster than I expected. We'll talk about energy utilization and scaling the laptop.
I have a question. So you use longitudinal data because, of course, like at the baseline, and then also at during the pregnancy, and then after the pregnancy to predict the individual risk. But because this is the final goal is support the decision, of course. So the key question for, when we support a clinical practice to make a decision, they will expect we can predict as early as we can, right? The model can predict for example, 6 weeks in advance or 6 months in advance. So I wonder when you conducting the predictive modeling, are you consider the time, how far the data you use apart to the event actually happened?
Yeah.
Did you identify the gap, how long the time interval, the data you use between the events happened?
I mean that's the beauty of the feature engineering approach, where you start with choosing the features that you want to use, as opposed to just taking the raw data with all kinds of trouble here. You can select your features specifically limiting yourself, let's say, to only 3 parts only. You can select your features based on the time when they can be obtained, and that will automatically limit you by design to, let's say, pre-partum information only, right? And then, so we've done it. I can show you. We have a few papers out doing exactly this for rehospitalization risk and post-partum depression, and that was exactly the exercise. Start with a few features only, such as BMI, smoking, insurance. What else was there? So basically it. And so what does that do? And this is pretty easy to obtain, right? You can argue that you almost don't need to mark for that.